Hello everyone and welcome to this brief introductory video. Today we'll be talking about quantum ghost imaging and its applications to the radar technology. The basic idea of ghost imaging is that we create a couple of position correlative photons with, for instance, a BBO crystal, and we send one to the object and the other to the camera. The object we want to capture has some holes in it, so some photons will be reflected but others can pass through and be detected by what is called a bucket detector. This detector is a big single-pixel camera, so it only registers whether a photon has gotten through or not. However, we would like to know where the photon has got through, and that way it comes the other array of detectors or a camera. Since the photons are correlated in position, what we can do is that whenever we detect a photon at the bucket, we can capture where the other photon is detected on the array, and by combining both informations, we can reconstruct the image. There are other variations of the technique, however. For instance, we can create two photons that are not only correlated in position, but also have different wavelengths. So, if we work in the infrared regime, some materials, such as the silicon, are transparent to the working wavelength, that is 1.5 microns, and we don't need to have holes in the object to capture the images. Other advantages of working at the infrared wavelengths is that it can see through smoke and tip the glass. However, this is not strictly a quantum technique. Although we use parametric time conversion to create the photons, we have only used its correlation in position, which is a classical correlation. So we can simply use a classical source, and that's what it's called a classical ghost imaging. Here, what we can do is to create random patterns and illuminate the object. And then we measure with a photodiode how much of these patterns overlap with the object. So if the pattern is very similar to the object, we get a huge signal, and if it's very different, we get almost nothing. Also, notice that here, instead of measuring the photons that went through the object, we measure the backscattered ones, and this can also be used with other ghost imaging techniques. However, instead of generating the patterns physically, what we can do is do it digitally, and that's what is known as computational ghost imaging. If we do that with a computer, we can know at all times which is the pattern that we produced. And now what we can do is to add all the patterns together using as a weight how much similar the pattern is to an object. And if we normalize the result, we can get the image of the object. With a projector, we can do as much as 22,000 patterns per second, and it only takes 80,000 patterns to get a pretty good image, so it's faster than the other methods. Finally, here is an example of quantum ghost imaging using correlative photons. Remember that these photons that are being recorded do not interact with the object itself. Meanwhile, I explained to you another variant of ghost imaging that I find pretty interesting. That is that, since the photons are entangled, we can take advantage of it and implement a process similar to the BB84 protocol of quantum key distribution. By doing that, we can ensure the integrity of the imaging process and make sure that no eavesdropper manipulates the photons that we get. Finally, some important advantage of quantum ghost imaging is that it is able to create the images of objects with much fewer photons or in spaces with low visibility. For instance, an iPhone uses 10 to the 10 photons, but with this technique we only need 10 to the 5. Also, it can have a huge impact on radar technologies, as we will see now.
After this detailed explanation of quantum ghost imaging, let's recall the principles of radar technologies, or LiDAR ones, as ghost imaging has become a breakthrough at the state-of-the-art integration in new generation of localization problems. In particular, we will now discuss one approach in the field of astronomy, led by Caltech Jet Propulsion Laboratory. The motivations for the research lie in its simplicity and robustness. A single pixel sensor can be used in the object channel, allowing us to focus in the advanced optics in the reference channel, making it ideal for imaging hard-to-access objects like distant planets. Additionally, coincidence measurement offers greater noise resilience than direct intensity measurement. The first of them is the ability to perform ghost imaging with thermal light, as most natural illumination sources in our universe, for example the stars, generate thermal light. In second place, it was shown that the bucket detector in the reference arm, which is nominally expected to collect most of the light scattered from the object, could be replaced with one that collects only a fraction of the field scattered by the object. These two conditions together permit an object to be placed at a large distance from the observer, which is critical for astronomical applications. and which also allow the detector in both arms to resemble point-like detectors, as interstellar distances result in large speckle sizes on the detector planes. However, using a thermal light source brings out a new complication. In general, a beam splitter has to be placed between the source and the object to create correlated speckle patterns in the signal and reference arms. While this is not a challenge in the laboratory environment, it becomes problematic when the source and the object are located far in space. The research carried at Caltech focused on addressing this beam splitter issue. The main idea of the proposed system was that an object which partially transmits or diffracts and partially reflects or scatters light can itself play the role of the beam splitter. Moreover, even a perfectly opaque scattering object may, under certain conditions, create coherence between the transmitted and scattered light, which may be used for the intensity correlation imaging. As you can see, and I told before, this approach leads us quite away from canonical ghost imaging, since the object is present in both. Moreover, in this study, two relevant further considerations were taken into account. On the one hand, it was assumed that the source properties were known, and instead focused on the parametric variation of the intensity correlation signature, as a function of the object geometry and localization relative to the source. On the other hand, it is also worth considering the case when both detectors receive transmitted and scattered light. This case is more realistic when both observers are ground-based and the distant source and object cannot be optically resolved. Therefore, the potential space objects of interest of this application will include Earth-like planets, including those near bright stars, gravitational lenses formed by black holes or other massive objects, but also dust or gas clouds. In fact, it was successfully tested in the Kepler extended mission between 2013 and 2018.
So now I'm going to talk about some applications. In traditional LiDAR system, the laser illuminates a specific area, but the system does not capture spatial resolution within the illumination area itself. This means that the information acquired corresponds to a single pixel at a time, such as the presence of a target, the distance, or the Doppler shift. To create images or maps, traditional LiDAR requires scanning the beam across the scene, which increases acquisition time and complexity. In contrast, quantum ghost imaging offers spatial resolution within the illumination area itself. This eliminates or reduces the need for beam scanning, enabling potential improvements in efficiency for applications like imaging through opaque media like smoke or fog, or under low light conditions. Despite the advantages of QGI, it faces some challenges. The first being the acquisition time. Achieving a high-quality image requires collecting and averaging a large number of samples. In computational ghost imaging systems, the number of light patterns needed to reconstruct a fully sampled image scales with the total number of pixels in the image, making the acquisition time inherently slow. Moreover, there's a trade-off in speed and quality to increase the frame rate of QGI systems. So on the one side, we have shorter acquisition times, which can be solved by using faster spatial light modulators like optical phase arrays to project quickly patterns. And on the other hand, we have reducing the required patterns, which can be done employing strategies like comprehensive sensing or orthogonal sampling, which use fewer measurements to reconstruct images. Research nowadays focuses on enhancing QGI performance in two main ways. The first is by optimizing illumination patterns by means of designing patterns that maximize the information content for better reconstruction. And the second is by developing advanced reconstruction algorithms that extract high-quality images from fewer or noisier measurements. Now we jump onto the second and last application, which is imaging. So in classical optical images uses light to capture images of objects or tissues, and it involves in illuminating the subject and detecting the light that is either transmitted, reflected, scattered, or emitted by it. However, imaging in a complex medium such as atmospheric turbulence, atmospheric scattering, underwater, or in biological tissues, scattering has always been a key problem to overcome in optical imaging applications. This is because the light signal becomes distorted or scattered during transmission or reception. These distortions can degrade image quality, making it hard to resolve fine details or detect objects. So QGI has unique properties that will make it well suited for overcoming these limitations. So since QGI relies on correlations between photons or light patterns instead of direct image reconstruction, it is resilient to medium disturbances. By analyzing correlations, QGI is less sensitive to distortions caused by turbulence or scattering along the light path. Moreover, underwater environments are particularly challenging due to the high attenuation and scattering, but QGI has been successfully demonstrated for imaging objects up to 9.3 attenuation lengths. And finally, here we jump on the conclusions. So the core principle of QGI is that it leverages correlation between pairs of photons or light patterns to reconstruct images instead of relying on direct image formation. There has been many advances over classical methods, for instance, the resilience to disturbances, energy efficiency, or advanced applications. However, there are some technical challenges that need to be overcome, such as the acquisition time or the speed-quality trade-off. And now we can see that the QGI has been integrated with space and radar technologies.